how, what equations can you use, how can this be done. So I'll start with the following example. A forest graph contains 10 trees. It has 5 vertices of degree 10, 8 vertices of degree 7, 10 vertices of degree 3, and the rest of the vertices are leaves. Find the total number of vertices. So let me write this down. A forest graph contains 10 trees. It has 5 vertices of degree 10, 8 vertices of degree 7, 10 vertices of degree 3, and the rest of the vertices are leaves. Find the total number of vertices. All right, so let's start by introducing notations. So the fact that we have a forest graph means that we have several connected components, in this case 10, so 10 connected components in a disconnected graph. And each of these connected components is a tree. So we need to somehow convert this information into an equation. If we just had a single tree, then we know that one of the most important characterizing properties of a tree is that the number of edges equals the number of vertices minus 1. And if you add to this that the graph is connected, then it's equivalent to saying it's a tree, right? So it's the most important quantitative characterization of a tree. Well, here it's a little bit different, so we cannot straight away write this equation, right? Because we don't have a single tree, we have a forest. But let's see what can we say about the total number of vertices and edges in a forest. So we'll start by introducing the numbers of vertices for each individual tree. Right? So let V1, V2, and dot 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 V10 be the numbers of vertices in tree 1, tree 2, and so on, up to tree 10, right? So imagine that we labeled our individual trees by some label. It runs from 1 to 10, and then there are V1 vertices in the first tree, V2 in the second, and so on. And similarly, let E1, E2, E3, and so on, up to E10 be the numbers of edges in tree 1, tree 2, and so on, tree 10. So since each one of them is a tree, we can use the standard relation between edges and vertices for each component. Okay. So we can write that E1 equals V1 minus 1, E2 equals V2 minus 1, E3 equals V3 minus 1, and so on. The last equation we can write is E10 equals V10 minus 1. Well, we kind of were led to this by the information at the beginning of the problem, right? So we have 10 trees, and we know how we can numerically characterize each of these trees. So we're forced to introduce all of these variables, but ultimately we are not really interested in in how the vertices are split between individual components, right? So the question we should target answering is find the total number of vertices. So to arrive to an equation which contains the total number of edges and the total number of vertices, I'll add up these 10 equations. And by adding up equations, I mean I'm separately adding left-hand sides and the right-hand sides. So adding up these equations we obtain. So on the left-hand side, we'll have E1 plus E2 plus dot 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 plus E10. So summing up the left-hand sides. And on the right-hand side, I'll have V1 minus 1 plus V2 minus 2 plus dot 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 plus V10. Sorry, V1. Oh, why did I say V2 minus 2? I don't know. Sorry, it's V2 minus 1, of course. Plus dot 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 V10 minus 1, always minus 1. And we can introduce a separate notation for the total number of edges in our forest graph. So let that be E without an index. So then the total number of vertices will be the sum of the individual numbers, V1 plus V2 plus and so on, V10, that's V. Right? And then there are as many minus 1s as we had equations, so that gives us minus 10. Right? So by adding up these equations, we obtain that in a forest graph with 10 connected components, the number of edges equals the number of vertices minus 10. And you can see, in principle, this is so general, this is easy to generalize. If we had a forest, say, with 25 trees, then the number of edges, the total number of edges in that forest graph will be the total number of vertices minus 25. Okay. So, all right, so that gives us a handy equation which connects the total number of edges and the total number of vertices. And I'll label this as equation 1, right? Because we only used so far this information that we have a forest graph with 10 trees. So what are we given next? So we're given degrees, right? So we have 5 vertices of degree 10, 8 of degree 7, and so on. So when you think about degrees, you should be thinking about the handshaking lemma, right? Because that tells you it's an equation which contains degrees of the vertices. So how will that look like? So the handshaking lemma, it will be my second equation. Handshaking lemma gives, so on one side I have sums of degrees of all vertices. So let's start summing them up. So I have 5 vertices of degree 10, so this will contribute 5 times 10 on the left hand side, plus we have 8 vertices of degree 7, that will contribute 8 times 7, plus 10 vertices of degree 3, 10 times 3, and the rest of the vertices are leaves. We don't know how many. So let's introduce a variable for that. Let's capital L be the number of leaves in this tree. Let's write then plus L times 1. Leaves, they have degree 1. So just L. And that equals twice the number of edges. True for any graph. Tree or not tree, right? Absolutely, in any graph, this should be true. So this is what the handshaking lemma gives, and let's just write for ourselves that where L is the total number of leaves. Okay? Any questions so far? Everybody understands why I wrote L times 1? It's because leaves have degree 1, right? And there are L of them. Okay, so what have we got here? So we have 2 equations now, and they involve, unfortunately, 3 variables, right? They involve E, capital V, and capital L. So we need at least as many equations as there are independent variables, right, to be able to solve that system. So we need more equations. Well, something which is always there in any graph, so call it equation 3, is just the split of the vertices into leaves and internal vertices. Right? So we can always write V equals L plus I, where capital I is the number, or the total number of the internal vertices. All right, that doesn't help much. It's always there, so it's always good to write things which are always there. But we've got a new equation and yet a new variable, capital I. All right. So we have 4 unknowns, V, E, L, and I, and 3 equations. So let's think, what else can we write? So something which would involve the number of internal vertices. And that's kind of hidden here, right? But in this information we were given, we actually were given the total number of the internal vertices. Because we're told that there are 5 vertices of degree 10, so certainly those are internal vertices. So there are 5 internal vertices of this type, 8 internal vertices of that type, 10 internal vertices of that type, and the rest of the vertices are leaves. So therefore they are not the internal. So we are actually given the total number of the internal vertices. We just have to add up the different types. So there are 5 vertices of degree 10. So I write 5 here, plus 8 vertices of degree 7, plus 10 vertices of degree 3. So the number of internal vertices is 5 plus 8 plus 10, which equals 23. All right? So leaves are degree 1. Anything which is not degree 1 is an internal vertex. Right, now we're in business, right? Because we have 4 equations and 4 unknowns. So we can solve this system, and it can be done in various ways. It's just a matter of convenience, but here nothing fancy needs to be used. Just direct substitutions can give you the answer. So that's how I'm going to do it. The equation 4 just tells me it's the simplest equation. It directly tells me the number, what one variable is. So it tells me that it is I is equal to 23. Therefore, I substitute that value everywhere I see capital I, and I see it only in equation 3. So from equation 3, V equals L plus 23. And, well, I can either substitute this expression into everywhere I see V, or I can solve it for L and substitute into the remaining equations. So that's what I'm going to do, because I know that I want to solve for V. It's not really important, but why not follow some logic? So I will solve for L. So L is V minus 23, and then substitute these in, well, L only appears in equation 2 in the handshaking lemma, into equation 2 to get. So in equation 2 I can sum up these terms, 5 times 10, 50, plus 8 times 7 plus 10 times 3, and that gives me 136. So I get 136 in that sum, plus L, and instead of L, I'll substitute V minus 23, and that is equal to 2E. So that's another relation in addition to the first equation, right, which relates to variables V and E. So let's copy equation 1, E equals V minus 10. So that's my system of simultaneous equations. And so just brushing this up, I get on the left-hand side of the first equation V plus 113 is equal to 2 times e, and substituting e from the second equation, I get 2 times v minus 10. So now it's a single equation which contains only v. So moving v to the right hand side and all the numbers to the left hand side, I get 113 plus 20 equals 2v minus v, which is v. And therefore, I get the answer, v is equal to 133. And yeah, that's the answer to the question we were asked. Any questions about this solution? Is the logic clear? Okay. If there are no questions, let me do another example. So this I call a spam email problem. So imagine the following situation. There's a spam email which is sent around, and initially it is sent to 5 people. And the email asks to propagate it further and to send it to 5 friends or acquaintances. And so some people really fall for it, and then they send to 5 friends, but others they just delete it. They don't do anything. And it's known that the email stops spreading after a certain number of people. So here's the number given: 366 people received it, including the first person who sent it out. And it's also known that nobody received this email more than once. The question is, how many people received the email but refused to send out the copies? So that's kind of a model situation, and the first question is to recognize that it's a problem about trees. So you can think that the first person who sent out 5 emails corresponds to the root of a tree. And then there are people who decide to, yes, they will send it to 5 friends. They correspond to internal vertices. And people who decide to delete it and don't send out any copies, those are leaves, right? And well, you might, if we had a situation when one person received the same type of email from 2 different people, that would spoil the property of having a tree. But we're told specifically that nobody received the email more than once. In real life, it would be a model assumption, right? That it's a tree. So if you think that everybody sends it to random people, then just because of the randomness, there are no such coincidences that somebody received it more than once. It's a very rare event. So for all practical purposes, we could assume that it doesn't happen. So it's a tree. But here we are told actually that doesn't happen. So we have a tree here. Moreover, we have a special type of tree. So what we have is a full fivery tree, right? So we discussed binary, ternary, and emery trees. So here this m, that number is equal to 5, because each vertex will have either exactly 5 children or no children. Then it's a leaf. Right? So let's write this down. So I'll write down the condition of the problem. So the spam email is sent initially to 5 people. Some people send it to 5 more people. Others just delete it. the email stopped spreading after 366 people received it, including the first person who sent it out. Nobody received the email more than once. Received email more than once. How many people received the email but refused to send out? Refused to send out the copies. How many people received the email but have not sent out any copies? Those who deleted it. Question mark. Okay, so that's the condition. And I talked you through the setup in which we recognize that we have a full five-array tree. Let's write this down. Here we have a full five-array tree. And so let's introduce numbers of various quantities. So E, the number of edges, is the same as the number of emails. So let E equals the number of emails. And then we have vertices, right? So that's the total number of people. And we're told that we have 366 people, including the first one. So that's the total number of vertices in this five-array tree. So V equals 366. The total number of people who received this email. And then we are interested specifically in people who received it but did not send out any copies. So those will be the leaves, right? So L, the number of leaves in this graph, is the same as the number of people who did not send out any copies. And we also have internal vertices, which the number of internal vertices will denote by capital I. That's the number of people who did send out copies. Who did send out copies. Okay, so we've introduced notation for everything. And now let's try out some equations. Okay, so one equation we already wrote, and we can denote it as equation 1. So V equals 366. That's an equation. Secondly, something which is always true in any tree is that the number of edges, E, equals number of vertices minus 1. Right, so that's true for any tree. we have not just any kind of tree, but a full five-array tree. And in such trees, there's an additional relation. The number of edges, the total number of edges equals 5 times the number of the internal vertices, right? So let's just remark, because we have a full five-array tree. Good. And finally, something we use in the previous problem as well, something which is always true, it's just that the total number of vertices equals the number of internal vertices plus the number of leaves. Okay, and now we're checking ourselves. We have 4 equations, and we have 4 unknowns, V, E, I, and L. So we can find everything we want, but it's worth noting that we're asked to find the number of leaves. So we're asked to find the number of people who have not sent out any copies. So we're after L. So L equals question mark. Okay, I proceed in the same way. I can gradually keep reducing the number of variables until I arrive to a single equation with a single variable, which I want to be L. So I start with substituting V equals 366 into equation 2. So that gives me E equals 365. Right, then from equation 3, so that was from equation 2 I found this. From 3, we find that capital I equals E divided by 5. That's 365 divided by 5. Oh, I didn't write what this is. So it's some number. Oh, let me keep it as a fraction. And then finally from equation 4, L equals V minus I. And V is 366 and I is 365 over 5. And here I did my arithmetics at home, so that's 293. Okay. Any questions about this example? So in this count, well, so just to wrap this up, these counting problems, variables I introduced in each of the 3 problems, one that I did in the last lecture and the 2 problems I did today, the standard, right? So it's always E, V, I, and L. At least those 4 quantities are there, right? And so one should then convert every piece of information given into an equation. And always check yourself, just, is it enough equations or not, by counting the numbers of unknowns, matching, with the, and checking, comparing it to the numbers of equations. Once you have the same number of unknowns as the number of equations, you're all set to find everything you need to find. But every piece of information given has to be converted into an equation. Okay, all right. So if there are no questions here, then let me start with something new. Again, continuing talking about trees, but different aspects. So I'll talk about spanning trees now. Spanning trees. I'll start with a definition. So let G be a connected graph spanning tree of G is a subgraph of G that has 2 properties. So property A, it contains every vertex of G, that A contains every vertex So let me give you a concrete example of a graph and a spanning tree. So my graph will contain 5 vertices. So that's my graph G, certainly is connected. And a single graph typically can have a large number of many different spanning trees. So here are some examples of spanning trees. We can obtain them by removing certain edges, keeping the graph connected. That will ensure that it's a tree, right? And also making sure that every vertex is in the tree. For example, I can remove AD, BD. It will give me a single loop, single circuit, which will involve all the vertices, so still connected, but in trees there are no circuits, so I can remove any one edge from that resulting circuit. For example, AB. So removing AB, AD, and DB, we get this kind of shape. A, B, C, D, E, right? Which has both properties. So it still has the same number of vertices as in the original graph, the same 5 vertices, and it's a tree, right? We can see easily. But that's not the only way to do it. For example, removing AD, CD, and DE, we'll get a different shape. We'll get this kind of tree. A, B, C, D, E. Still there, right? So again, it has the same 5 vertices and it's a tree. So it's a spanning tree. And I'll give you one more and then we'll move on. C was CDE. So here we remove AB, AC, and BE. Right, and we obtain this spanning tree. So, where a spanning tree is important? They're important in constructing networks. For example, if you have, you want to build a network connecting a certain number of nodes, and suppose your regional graph represents possible connections which you can build, right? But you want the absolute minimum number of connections, so that each vertex is connected to each other vertex by a single path. And we know that that graph then, with absolute minimal number of connections, must be a tree. And if it is to connect the nodes in the original graph, then it has to be a spanning tree. So there are various options. One can then assess them using any other information. Which one is better? It depends on the context, right? But finding a spanning tree will provide a minimal number of connections in a network. Another example of where spanning trees are used is in internet spiders. or internet crawlers, those are programs which index all the web pages in the World Wide Web, and there they have to reach every web page to access it, and they only want to make it once. So typically it's done in the form of a spanning tree. So they travel along the legs of a spanning tree back and forth, collect information, and then come back to the root where everything will be actually stored. Okay, so it's an interesting problem with various applications, constructing a spanning tree. I'm going to present two different algorithms. One is called depth-first search, another one is called breadth-first search. So these algorithms construct spanning trees for a given graph. But before that, I want to do one more counting problem, just to kind of again, practice a little bit before the algorithms. So here comes an example. So here I'll talk about complete graphs. I don't think they were mentioned yet in this course. So I'll start with the definition. A graph with n vertices is called a complete graph and is denoted as K sub n if there is one edge between every pair of distinct vertices. For example, if you have three vertices, right, and you just connect each pair precisely once, that gives you the complete graph K3. If we have four vertices and connecting each vertex to each other vertex, will give us this graph, which is K4 in our notation, right? And so on. So you can draw, if you wish, K5 or K6. And so this brings me to my question. How many edges need to be removed from a complete graph K500 to obtain a spanning tree? How many edges need to be removed from the complete graph K500 to obtain a spanning tree? Okay, not a hard problem. So let's first figure out how many edges we do have in the spanning tree K500 with 500 vertices. So it's a complete graph with 500 vertices. Then let's find out how many should be in the spanning tree, and then we'll take the difference, that will be how many we have to remove. So in K500 we have 500 vertices, and each vertex is connected to each other vertex, right? So you can think that if you want to count the total number of edges, it's like counting the distinct pairs, right? Or the same as counting all combinations with two elements from the given set of 500 elements. Because I pick two vertices from the set of 500 possible vertices. And they have to be distinct, so it's a subset, and the order in which I pick doesn't matter. So those are combinations. So it's not hard to count them. K500 has two choice 500 edges, right? So it's 500, this can be simplified to 500 times 499 divided by 2 edges. And if you use a calculator, that will give you 124,750 edges. Right? So here I used something we did in combinatorics, right? The binomial coefficient for choosing two distinct elements from 500. Okay, so that's how many our how many edges our graph has. And what about the spanning tree? So we know that all the vertices, all the 500 vertices which were there will have to be used in the spanning tree. And since the spanning tree is a tree, we have a relation between the number of edges and the number of vertices. So the number of edges will be the number of vertices minus 1. So spanning tree with 500 vertices has 499 edges. Therefore, or hence, the difference 124,750, that's how we had initially, minus 499, that's how many we want to get in the end, equals 124,251. That's the number which needs to be removed. Need to be removed. Okay, so just again, an example of a simple counting problem. Any questions? Yes, please. No, by definition, spanning tree must have all the vertices there from the original graph. So we cannot remove, we should be careful removing edges. So we only should remove edges for which there are other edges still remaining which contain those two vertices. Right? So we should always keep the graph connected when removing the edges. So this is in the algorithm. I'll talk about how to construct the spanning tree, but yeah, in principle, yeah, we should be careful not to remove any vertices when removing the edges. Right? We know when we construct a subgraph, if you remove a vertex, right, then you remove all edges ending on it as well. But yeah, if you remove the edges, the vertices stay there, but what can happen, suddenly it can become disconnected, right, if you remove the wrong edge. Right? So one should stop at the right point. Okay? Anything else? Yes, please.
Yeah, why did we use the letter K?
Just conventional. Yeah, we could have used the letter C for complete, I guess. But for some, I don't know, for some historic reason, there's this notation used in various books for complete graph. Yeah, no, yeah. C probably would be better for the word complete, but for some, I don't know why K is used. Anything else? Okay, then let's start discussing finding spanning trees. So here there are two, in principle there are two approaches. So algorithms for constructing spanning trees. So there are two approaches. So one is the cutting down method. So you literally, yeah, remove edges. So you pick, you find first a simple circuit. If it's not there, then the original graph is already a tree. Then it itself would give its spanning tree. So assuming that the original graph G is not a tree, there must exist in it a simple circuit. Then from that simple circuit we can remove a single edge. It would still keep it connected because you can go around the circuit in the other direction to connect between the two vertices, two affected vertices. So you get a new graph with smaller number of edges, and you ask yourself, is it a tree? Then if it's a tree, you stop. If it's not a tree, then there must be another simple circuit. You identify it and remove one edge from it and keep going. So that's one strategy. So this is called the cutting down method. So pick a simple circuit, if present. If not present, then you stop. Then remove an edge from this circuit. Right. Keep going until you arrive to a tree. So we never remove vertices, all vertices will be there. So here's one example of a simple circuit. Maybe connected to the rest of the graph in some way. So any edge can be removed. Right, and that will not make the graph disconnected, right? If you're removing only edges belonging to some simple circuits. Okay, so it's a valid strategy, definitely will give you a spanning tree, because you're bound to stop at some point, right? Because the number of vertices stays the same, so and the number of edges will be gradually decreasing, because we will be removing edge after edge, and then once the number of edges equals to the number of vertices minus 1, then it has to be a tree. So that would be a spanning tree. So it's a valid strategy, but it's not an efficient strategy because it's hard to identify simple circuits. You have to search the entire graph to identify the simple circuits, and it's time consuming. Yes? Spanning vector. What's a spanning vector? Oh, when you're looking at linear combinations. Yeah. We're spanning vectors by given number of vectors.
Yeah, so the spanning tree, is it more like you can shield, is it like the smallest tree you have on the
I don't immediately see the connection. So there's something from linear algebra. Indeed, there's this, spanning is the word used in linear algebra when you look at all possible linear combinations of given vectors. I don't immediately see any connection between this linear algebra spanning and trees. I don't see any trees. Are you thinking like the vectors correspond to vertices or edges? Never heard of it, so I have to think about it. I mean, it would be cute if there was some connection, but I have to think about it. Yeah, nothing immediately kind of brings to mind. Right, so let's just write down that this is not efficient because it's hard to identify simple circuits. Oops. Simple circuits. So another strategy is called building up methods. There, we actually build our tree by adding edges from the original graph, right? And so we should ensure that at each step, when adding a new edge, I'm not creating any new simple circuits. And I know also when I should stop. I should stop when all the vertices will be in my tree, right? That will be a spanning tree. So there are two different algorithms which I will discuss on the next lecture, which use this building up strategy. So the depth first and the breadth first. Right, so I think now is a good point to stop. As usual, I'm going to scan and upload